Training a modern large language model requires thousands of GPUs firing simultaneously within a single cluster. This density creates intense localized heat as these processors cycle through the billions of parameters necessary for deep learning. For the last decade, enterprise IT strategy relied on a simple principle: lift your workloads and shift them to a centralized public cloud. Applied to sensitive AI workloads, that strategy collapses. Pooling proprietary enterprise data into external, centralized data lakes creates severe compliance liabilities. Under frameworks like GDPR and the EU AI Act, exporting localized, sensitive data out of a sovereign region risks significant legal and financial penalties. Public clouds are structurally designed for shared infrastructure. They lack the hardware abstraction necessary to enforce impenetrable jurisdictional boundaries around a single tenant's data while it is being processed by an AI model. Securing enterprise AI requires the complete abandonment of the centralized data lake model. The architecture must bring the model to the data, rather than exporting the data to the model. This requirement introduces the sovereign AI cloud, a private, virtualized ecosystem operating entirely on hardware owned and controlled by the enterprise. A true sovereign architecture operates in a disconnected, air-gapped environment, or through a strictly controlled network state with zero unauthorized external access. This schematic shows the architectural divergence. On the left, the public cloud model forces raw data to stream constantly into a centralized hub. On the right, the sovereign model keeps those green data paths local to the enterprise. Only the model's parameters travel out to the edge. The proprietary data remains entirely Serlic inside internal silos. The AI interacts with this data to learn and refine its weights, but the raw information never leaves the local server environment. Keeping data locked on internal hardware ensures the enterprise retains total control over its intellectual property. The model learns the organization's trade secrets without ever transmitting them to an external vendor. Regulatory compliance is a byproduct of this design. The primary achievement is a re-engineering of the AI data center to prioritize absolute data isolation. To build an independent sovereign AI node, we have to start at the physical layer and define the exact hardware required. The baseline requirement is absolute physical ownership of the infrastructure. You cannot guarantee a defined jurisdictional boundary if you do not own the silicon processing the data. Once the physical servers are secured, the system requires the immediate capability to integrate and train large language models directly on that local hardware. The engineering hurdle is hardware dependency. Traditional IT stacks rigidly tether a specific software application to a specific physical GPU, leaving massive amounts of compute power idle when that single application isn't running. Overcoming this requires an operating system built on hardware abstraction and GPU virtualization. Virtualization breaks the strict one-to-one bond between hardware and software. By mathematically segmenting a single physical GPU, the system can route isolated fractions of its compute power to multiple virtual machines at the exact same time. This creates dynamic resource provisioning. If one virtual machine goes dormant, the infrastructure automatically contracts that data pipe and shifts the available GPU power to an active AI workload experiencing high demand. Decoupling the operating system from the physical hardware is the mandatory first step to making localized AI operations financially viable. With the local hardware abstracted, a new constraint emerges: training a large AI model across isolated servers without network exposure. The solution is federated learning. This paradigm reverses the mechanics of traditional machine learning. In step 1, the central orchestrator pushes copies of the global model down to the isolated edge clients. In step 2, the clients execute local training. They train the model exclusively on their private datasets. The local files remain perfectly static. In step 3, only the resulting mathematical weight updates, the gradients, travel back to the central orchestrator. The raw data is left behind. Standard algorithms like federated averaging work well for uniform data, but heavily skewed enterprise environments require optimization-aware algorithms like FedProx to stabilize the training process across diverse client data. Federated learning solves the data privacy problem by executing the math where the data lives. Federated learning protects the raw databases, but a critical vulnerability remains. The raw gradients traveling back to the server can be intercepted and subjected to reconstruction attacks. During the transit phase, a hostile adversary node can intercept the raw mathematical matrix. Using advanced inference techniques, they can reverse engineer those weights to reveal the exact training samples used by the edge client. Neutralizing this threat requires a primary cryptographic shield, known as homomorphic encryption. Homomorphic encryption allows the central server to mathematically process the gradients while they remain entirely encrypted. The server aggregates the data without ever possessing the decryption key to open the plaintext parameters. To protect the specific identity of individual clients, the architecture applies a secondary layer, secure aggregation. Secure aggregation masks individual contributions. The server only perceives a collective mathematically mixed update from a cluster of clients. It cannot isolate or identify any single node's input. Synthesizing federated learning with homomorphic encryption and secure aggregation establishes strict mathematical guarantees against data leakage. Translating these theoretical algorithms into practical systems engineering requires a unified software-defined infrastructure, such as VergeOS. Deploying this architecture onto internal enterprise hardware follows a specific 5-step deployment framework. Step 1 is assessment and planning. Engineers map the existing hardware gaps and enforce strict jurisdictional network boundaries. Step 2 deploys the unified infrastructure OS. This collapses independent compute, storage, and networking silos into a single software layer. Step 3 expands resources. The system integrates dedicated AI hardware and enables the GPU virtualization protocols to optimize power allocation. Step 4 auto-deploys the large language model. The system spins up an open-source model as an internal service, ready to ingest and fine-tune on proprietary datasets. Step 5 automates and scales. Intelligent workload orchestration applies multi-tenancy rules, segmenting the AI into isolated virtual data centers for different internal departments. Utilizing a unified software-defined infrastructure collapses the overwhelming complexity of sovereign AI deployment into a repeatable process. Once deployed, the architecture must pass a rigorous security audit to verify its defenses. The first mandate is to verify air-gapped connectivity. If the system can freely communicate with the public internet, the jurisdictional boundary has failed. The system must enforce network isolation and utilize virtual data centers to prevent any unauthorized lateral movement from one internal department's workload to another. The environment requires a zero-trust architecture. The system must demand identity verification for every single internal data access request, assuming threats already exist inside the perimeter. Finally, on-the-wire encryption must be active across all 3 operational stages: data in storage, data in transmission, and data during computation. Enforcing these architectural guardrails separates a true sovereign AI from a vulnerable, standard on-premise server. The practice of lifting and shifting sensitive enterprise data into shared public cloud environments is structurally obsolete for modern artificial intelligence. By combining strict hardware abstraction, federated learning, and advanced cryptographic shields, enterprises can build a fully sovereign alternative. This shift replaces the previous era of cloud strategy with architectures that assume distribution and intelligence from day one. Instead of retrofitting old models, organizations are building systems around the specific requirements of AI. We are moving toward a distributed network of secure, independent intellects, operating locally but scaling globally. Sovereign AI allows enterprises to harness the full analytical power of cutting-edge intelligence while maintaining absolute, uncompromised ownership over their most valuable intellectual property.